John, over to you.
Thank you. Okay, so a little bit of introduction about myself. You'll see there it says John Barton and one of my roles, but just a bit of background so that you know where I come from. I trained as a primary teacher and spent many years teaching in primary school, but maths was my background, my subject, and what I really enjoyed doing. I then moved into adult education, initially not in maths, but very quickly moved into the maths area and was involved there in teaching maths, and then into a post-16 college teaching post-16 learners. I became a manager and a teacher trainer within the college and worked for there until I retired. And also for quite a number of years now, I've been chair of NANAMIC, the National Association for Numeracy and Mathematics in colleges, though we're actually involved in all sorts of areas, not just colleges, any post-16 area. So that's a little bit of the background of me. Just to say before I start, I watched the keynote this morning with Fiona, and you will notice some similarities here. I've known Fiona for many years, and I won't be going on to the main part of what she was saying, but certainly there will be some things in what I cover that were mentioned by Fiona regarding good teaching, and that's a good thing. So I want to start out, first of all, with the first lesson and what happens in the first lesson, because I discovered something quite by accident. As I say, I was a manager as well as still doing teaching, and I had a particular problem just before I was due to teach a brand new group, and so I hadn't been able to get the photocopying done. Wasn't organised. It helps us all to admit at times that we don't do things exactly as we should. And so what I said, there was a photocopier right outside the room. There were big windows in the side. There were post-16 anyway. And so I said to them, before we start, what do you think of maths? Discuss it among yourselves. And I went out. I was only out for a couple of minutes, but I was able to see that there was quite a lot of discussion taking place. And when I came back into the room, I let that discussion continue. And from that point onwards, it's something that I've always done, is in the very first session, I say to them, discuss what you think of maths. And that helps me to get a good understanding of where they're coming from, what the background is. Because most of the learners that I was involved in teaching were ones who had not achieved the equivalent of GCSE pass level, and so they were having to resit maths. They'd had 11 years in school, all sorts of negative feelings towards maths from the vast majority of the students that I was teaching. So that was the very first lesson. But I want to say about 7 things that I found that have worked for me in engaging the disengaged learners. And the first thing is to use a non-calculation starter. Now, I've got a whole series of these, about 40 of them I had available to me. And these were things that could easily be introduced at the beginning of the session. One of the things that I would do quite early on, often in that first session, is the great race from We Can Work It Out by ATM. If you've not seen that, basically you've got these cards and they have various things on them, and you just give them the pack, and you don't tell them what to do, but you let them sort out what they've got to do, working in small groups, 3 or 4. So the cards, just some of the things there. The white car finished 6th place behind the blue car. The yellow car was in the middle of the order of finishing. The average speed of the race was 102 miles per hour, etc. But you'll see that there are 2 cards that are quite important. The top right says there are 9 cars in the race, and then on the second row, the second card in says find the finishing order of the cars. And that is the purpose of the exercise, to find the finishing order of the cars. And they had to sort it out. An interesting thing is that when presented with this, some learners say, but this isn't maths. And that's because they've got quite a distinct idea of what maths is, what's involved in maths. And they think that it has to be calculations, whereas actually maths is about thinking things through and is about looking for patterns and ideas. So what do you need to do? Well, you may need to support. I'm aware that some of you will be working with younger learners, some working with older learners. So it depends on your students. You may find that you need to suggest ordering pieces of paper marked with the colours, and they can write the colours red and yellow, and they can manoeuvre the cards around. But also within there are two cards which are totally irrelevant to sorting out the order. There's one which is to do with the average speed, 102 miles per hour, and another one which says it was raining. Both of those are totally irrelevant. And that can cause problems for learners, because they think, well, what are these for? They've grown up with the idea that every piece of information has to be used in coming to the calculation results. And so they need to learn that in the real world, there are lots of times when we have to ignore certain pieces of information. And this is quite important for understanding what maths is about. It takes it from sorting out the things which are not particularly relevant from the things which are. And that's very important for students to get that idea of maths from early on. There are other possible starters, some of which we're going to look through as we go through the presentation. Picking up straws, that's one of them. The Tower of Hanoi. This is the one where you have to get the rings on the left-hand peg to the right-hand peg by taking them off one at a time, but you can't put a big ring on top of a smaller ring. So for instance, if you put the purple one on the middle, you would then have to put the blue one on the right-hand side, and then the purple could go on top of the blue, and so on. The Tower of Hanoi. And it's trying to sort it out to get from one position to the other in the fewest goes. Obviously, you might want to start with perhaps 3 rings or even 2 rings and see if they can work out the pattern of how many goes it takes and the logical thinking to get from one position to the other. Frogs is another one that I'll come on to later. Try to give them simple printed instructions for them to follow so that you're not having to give them verbal instructions, but they're able to read what to do and to get on with it. So picking up straws. There are 41 straws on the table. Make sure that there are 41 in the pack. You can pick up to 5 straws each time you have a go. Your opponent can also pick up to 5 straws each time. The winner is the one who picks up the last straw. You can pick 1, 2, 3, 4, or 5 straws to win. It is possible for you to win every time if you go first. Can you work out how? And what if you could both pick up to 6 straws on each go, or 4 straws? What if you had only 23 straws? So they've got to come up with a strategy that works no matter how many straws there are and how many you can pick up each time. And in case you're wondering, if you think you had 6 straws and it was the other person's go, they can't possibly win, and you certainly can win. So you've got to work some principle to get you down to that position. So the second thing that has worked for me is to give them a reason for learning. Why learn? It's very important. I might say, I'm going to teach you Oshiwambo. Oshiwambo is a language which is spoken in northern Namibia and in southern Angola. And I might teach you some Oshiwambo if I knew some, but I don't know any. And I have no intention of learning Oshiwambo. However, my daughter-in-law speaks Oshiwambo. She comes from Namibia, and it's her native language, as it were, though she speaks English as an daily sort of language. But my son might want to learn some Oshiwambo because his wife speaks the language. So it's important that we have some reason for learning in order to be able to learn most effectively. Why learn? Why should I want to learn that? When I was at senior school, I had a friend who had a downer on science, and he hated science and saw no point in it whatsoever. And I remember when he did his mock physics exam for O-level, that he spent the whole of the session writing why he shouldn't need to study physics. Incidentally, years later, I found out that he'd become a professor. But there we are. I'm sure he didn't take that sort of view from his students. But it is important that we see a reason. And it's the same with maths. We learn best what we want to learn, like driving a car. Somebody who's learning to drive a car usually is wanting to learn, wanting to pass their test, wanting the independence that it brings, wanting the freedom that they get from being able to drive. And so they spend time learning, they put in their best effort. Whereas when it comes to maths, it's a lot of that negative aspect. Why? What's the point? And so we need to address that. And in the first lessons, one of the things that I do is ask them what they would like to be able to do in maths by the end of the year that they can't do now. Sometimes it's pass the exam, and I say, no, apart from pass the exam, what would you like to be able to do at the end of the year? And then I do my best to ensure that by the end of the year, they're able to do that calculation, to work it out. The third thing is to start with a problem, not a method. One of the things that happened when I was into management role and just before I retired was I was involved in consultancy work. And I went to see two particular maths teachers, completely different circumstances, but they were both delivering the same problems on area and perimeter. And the first one, she taught them how to calculate area and perimeter, and spent quite a bit of the lesson doing that, and then gave them questions to answer so that they could practice on working out area and perimeter. And I would say that that is a traditional way that many people have approached it. I'll teach them how to do it and then do lots of examples. The second one I went to had a completely different approach, something along these lines. York City is about to move into a new stadium. I live in York, by the way, and York City has moved into the new stadium. But if we go back a little while, it's about to move into a new stadium. They want to know how much grass they need and how long a fence to install. Now, by setting a problem like that, we can then go down, well, how are we going to calculate? What do we need to do? And we can see straight away that the learner is engaged in that process. They need to be maybe introduced to the terms area and perimeter, but they set about the problem and they have some understanding of what is involved because they see the purpose of it. It's not just some exercise that mathematicians like to create, some puzzles that they like to set for people then and to get students annoyed. No, it's about real life situations. And so wherever possible, start with a problem rather than the solution as to how to do it. The next thing to say is don't repeat what they already know. Now, it's important that we establish what learners know. So much time is wasted in repeating things. So we get learners who go from little school to big school, whatever stage that might be, whatever age, according to where we are living. And we find often that the teachers in the big school say, well, they didn't have the knowledge, so we started again. And they repeat much of what the learners have learned in the previous 6-7 years. And so much time is wasted in repeating things. The best thing to do is to find out their knowledge. A good way of doing this is by using posters. Now, a poster, we usually think of a huge piece of paper, and giving somebody a huge piece of paper and saying, okay, as a group, fill that in. Here are some pens, and write about what you know about and tell them the subject. But what I discovered, it wasn't my idea, but I liked it, was the idea of giving them a choice of poster size. So they can have a huge A0 size of paper, or an A1, or an A2, or A3, or even A4. And they can use that for writing down the knowledge, depending on how much knowledge they feel they have. And that helps them because they then start to see what they do know already. And it's important for you to understand what they already know. And then once we know what they know, we can build on that previous knowledge rather than having to cover what they don't know. It might be that we need to establish some things such as, you know, their good understanding of certain areas. But if we know what they know, we can deal with that quite easily. This also will reveal misconceptions. It's important that we deal with misconceptions. And we've all had them at some time or other in our maths lives, whether it was when we were very young or as we got older, we have had those misconceptions. Misconceptions are actually how we learn. We find out what the misconception is, and then we understand how to correct it. So I went on a course when I'd not done any teaching for a particular level, and I think when I was teaching in junior school, we didn't particularly do about segments and sectors and things like that. And so I'd not covered that, and we had to draw this poster, and one of the things to do was to draw a segment. And I drew what I thought was a segment. We discussed it as a group. We came up with the answer. And the thing was, it was wrong. It wasn't a segment, that was a sector. And I know exactly where I was when that happened. It was at the University of Sheffield. That was where the course was. And it's stuck with me ever since. I've never, ever got it wrong since that point. I now know the difference between a segment and a sector because my misconception was revealed. And that is helpful for learners. Then another thing is to use effective questioning, because it's not just about getting the right answer. Now, getting the right answer is important. I did have one particular learner who was about 17, 18, and he would work on a particular problem. It was in a functional skills, functional maths level. That's what he was going for. And he would do all the workings out and then not bother to write in the answer. And he took the view, well, you get marks for method. And I told him, yes, but you also get marks for writing in the answer. You do need to work out the answer. So getting the right answer is important, but it's how we get there that is important. So I want to consider another one of the maybe starter activities, which is how many diagonals are there in a polygon? So the problem I would set would be this: how many diagonals do these shapes have? How many do you think a 10-sided polygon, a decagon, should have? And then I present them with this. So you can see there that we've got 4 shapes, and at the bottom we've got the number of sides and the number of diagonals, and they have to fill in. the number of diagonals. So you'll see that I've actually asked them to fill in the results for 8 shapes, but I've only given them 4. So they should be able to work out that, of course, a triangle doesn't have any diagonals at all. And then they can start to fill in the next ones. So when they've done that, and I like to provide them with coloured pencils so that they can do that, so they can keep track of where they are, we can see that the chart below gives us some of those 0 to 5, 9, and often with the 8, they don't get 20 to start with. But when we ask them to see the pattern and to fill in the blanks, then they can start to say, well, 3 to 4 goes up 2, 4 to 5 goes up 3, 5 to 6 goes up 4, so 6 to 7 should be able to work out that that goes up 5, which will give us 14, and 7 to 8 goes up 6, which gives us the 20, and so on for the 19 and 20. So once they've done that, it's, well, the pattern, we can see the pattern there, but can we explain it? Now, traditionally, one way would be to find the nth answer. So, and we can actually see that n equals n minus 3 divided by 2, where n is the number of sides. But if we go back to the previous slide, we can actually see how we get that formula. So if we look at the pentagon for a moment, you'll see from each of the vertices, there are 2 lines, and only 2. So for a 5-sided shape, you can only have 2 diagonals going from each vertices. That's because you can't draw a diagonal back to yourself, and you can't draw a diagonal to the adjacent sides. So you can see it's always going to be 3 less than the number of vertices. So we've got 5, we've got 2 going from each one, 5 2s are 10, but we've only got 5 lines. And that's because, of course, each of those lines we're counting twice. We're counting one end and the other end. So we need to divide it by 2. So this is one case where they can actually see how we get to the formula. And the understanding is quite clear to them, finding the pattern. They can explain why. We need to encourage them to do that, to explain the reasons. Then for the 5th one, use collaborative learning. I believe that this is so important. Silence is not golden in maths. One of the people who was on my course used to teach maths to ESOL learners in Leeds. These were adults where English was not their first language, and he was teaching them maths. I used to love to go to his classes. This was a guy who actually was an academic who'd escaped from Iran. He had been an archaeologist there, and he'd escaped, come to Britain, but he had the ability to work well with his learners. And as I used to walk down the corridor towards his lesson, I could hear his lesson because everybody was animated, everybody was involved in the lesson. A lot of discussion was taking place. It was a wonderful lesson for learning English and for also learning maths. There is a place for individual work, and especially when preparing for exams and that sort of thing. But collaboration is key to understanding for most students. When they work with others, then they have to explain their reasoning, and this helps their understanding. I put in brackets worst lesson to remind me of the worst lesson that I ever went to see. I was running a course for learning, for teaching assistants, and most of the people on the course were members of my own staff, but one person who was on the course had recently got a job at a local high school, secondary school, and he was supporting them in their maths lessons. And so I went along to observe him supporting the teacher. And I am really glad that I was observing him and not the teacher, because it really was the worst lesson I had experienced, I had seen. Because what happened was the learners were given a piece of paper, they were given scissors, they were told to cut up the scissors, cut up the shapes with the scissors, and then to stick them in their books. And the various parts were words like acute, obtuse, right angle, and they had pictures of angles, and they had things like 0 to 90, 90, 90 to 180, etc. And they had to cut those out and stick them up into a grid in their books. And then it was when they had finished that, the extension activity for those who had finished was that they had a sheet with a line on, and it said something like it's 38 degrees, and you had to work out the other angle on the straight line. And the teacher actually said to them, the way that you do that is it's 180, take away the angle that I've written in there, and you can use your calculator to do it. That was a full lesson. They were not allowed to speak to each other. They just had to get on with their work. And what I found was that the students were misbehaving. I was an angel at school. I really was well behaved, but I would have been disruptive in that lesson. It was awful. And then to make matters worse, the teacher actually kept them back afterwards because they had been so disruptive during the lesson. Collaboration, I think, is key to understanding for most students. If those learners had been allowed to talk about what they were doing, I'm sure they would have had greater understanding, and they probably would have been finished in about 10 minutes. Getting to explain why their answer is correct, even if it isn't, is important. I taught apprentices who needed to achieve a certain grade of maths for their apprenticeship. And I got to the point where all the learners had passed apart from 2. So I had these 2 learners, and I got observed in that particular lesson. And it was interesting. We had done a mock assessment the previous week, and so we were going through that mock assessment. I didn't mark it, but we went through and asked them for their answers. And we came to a question where they got completely different answers. And so I said, okay, mention their names. You explain why yours is right. You explain why yours is right. And left them to do so. And as they started to explain, the one who got it wrong recognized the mistakes that they'd made. Didn't need me to go in there or put a red mark there next to it or anything like that. They were able to recognize the mistake and learn from that mistake and not make that mistake again. So getting them to explain their answer is very important. And then if you're doing an investigation with the learners, others might want to go in a different direction to you. So that's a good reason for collaboration. So you think in a particular way, they can think in another way, and you need to reach a compromise as to which way forward to go with the investigation. So I'm going to look at the one frogs. So here it is. There are 5 lily pads in a pond, and 2 red frogs and 2 green frogs are sitting on 4 of them. They want to swap so that the reds end up on the greens pads and the greens end up on the reds. They can hop from one pad to the next if it is empty, or they can hop over one frog of the other colour onto an empty pad. What is the least number of goes you can do it in? And so I'd start off with something like 5 squares and give them representations of frogs, probably unicubes. So a couple of red unicubes, a couple of green ones, and say, okay, how many goes can you do it in? Can you work out how to do it in the least number of goes? And once they were happy with 2 frogs on each side, then to make it 3 frogs on each side, and see if they can come up with a pattern. So what if it's 1 frog on each side, 4 frogs on each side? Can you start to see the way that the numbers go and the pattern that's involved? Now, that's great when we're dealing with small numbers, but what about larger numbers? What if we have more frogs? What if we have different numbers of frogs on each side? Well, Enrich have a program that lets us do just that. So here's the Enrich program. So it starts off with the 2 frogs. It uses reds and blues rather than my reds and greens, but we can swap the 2 frogs. So basically we can move either that frog to there or that one to there. So if we click on the 1 frog over that one into there, then we can see it says you have made 8 moves. Well done. You have swapped all the frogs in the minimum number of moves. Let's just have a go, reset that one again and see what happens if we don't get it right. So if I go like that, I then can't do anything with any of the other frogs. The only one I can move is back to where I started from. So I would then have to go through the moves again. This time it would say you have made 11 moves. You could have swapped the frogs in fewer moves. Have another go. Okay. But my question might be, well, what if I have 1 frog on one side and 3 on the others? If you remember, 2 and 2 came out at 8. What if I have 1 and 3? Okay, so let's have a go.
John, we can only see your slides at the moment. We can't see the frogs. Although Francesca has very kindly put in the chat the link to the website that you're currently on. We've got the whirling circle of doom on our screen.
Right. Sorry, I don't know why that doesn't work. Okay.
You might, John, you might need to change which window you're sharing. Zoom will share 1 window at a time by default.
Right. Okay. Right. Let's try that. Can you see now?
Yes.
Yep. Okay. Sorry about that, folks. Okay. So yeah. So I was saying you might want to try 3 frogs on one side and 1 on the other, and see if you get a different result. So let's do that. And we've seen this time it only takes 7 moves. So it's not related to the number of frogs. It is related to something else. And we can start to find out what the pattern is. Now, some learners would say, okay, let's go 1 and 2, 1 and 3, 1 and 4, 1 and 5. Others would say, well, let's do 2, 2 and 2, 3 and 3, 4 and 4, 5 and 5, and so on. So you've got different alternatives, but can they come up with a pattern that works for them? Okay, so let's get back. Okay, so the next reason that I've got is reasoning rather than the correct answer. I found this works very well indeed. We need to encourage reasoning, thinking things through. There are lots of students who think maths is all about getting the right answer. Getting the right answer is important, but it's not the only thing that is important. Understanding the reasoning behind it helps us to start to generalize. And I think the value of maths must certainly be more obvious to learners now than it has been for many years, because every day we're getting statistics, we're getting data, we've got scientists and other mathematicians who are working on the data and coming up with answers and predictions. But you still get learners who say, yeah, but what's the answer? I understand what I'm doing, but what's the answer? And we do need to just encourage them to step back and say, yeah, the answer is important, but we do need to think about how we can get there. So, for example, things like multiplication tables. There are those learners who will know their multiplication tables, no problem. But there'll be others who perhaps know 7 sevens are 49, but not know what 7 eights are. If they understand what is involved, then that can help them to get to the right answer. So they can do the 7 sevens are 49 and add on another 7 to get the 56. So they can do that quite quickly. They can develop those skills. If they have reasoning, it helps them. Another example for encouraging reasoning is division. Division is one of those areas where lots of learners have learned things like, well, it's round here in Yorkshire, they say goes into or goes into to translate it. So how many does it go into? How many times does it go into another number? How many times can you share it? And so you get people thinking of division in that way. So then they come on to something like 2 divided by a half, and they think that the answer is 1. But another way of thinking about division is to think of it as multiple subtraction. So, for example, if we have 2, how many times can we take half away? And of course, the answer is 4 times. And it makes a lot more sense. Whereas this idea of 2 divided by a half, well, you invert it, multiply, which is what I learned, didn't give me any reason for understanding what it was about. The equal sign has become the bane of the maths teacher's life. It's usually seen as what is the answer, even though they've probably been introduced into something like 6 equals box times 2 when they were quite young and they were able to work out that that was 3. But somehow over the years, they get used to the idea that the equal sign means the answer. And so you get things like this. And you place too much emphasis on the answer and too little on understanding. Somebody writes something like 3 add 4 equals 7 times 8 equals 56, which of course mathematically is an absolute load of nonsense, because it means that 3 plus 4 is equal to 56, which it definitely isn't, I can assure you. Okay, so I will have to hope that this works, and if it doesn't, please let me know. But this next one I've done a video of, and so we'll see what happens.
So take a sheet of paper and fold it into 3 equal parts. And keeping the paper folded, shade the part that is facing you. Keeping the paper folded in the same way, then fold it into 4 equal pieces. The question is, what fraction of the shaded part is facing you? And then, what fraction of the whole of the paper is facing you? So what is that as a fraction of the whole piece.
Okay, so there I was showing the idea that a quarter times a third is a 12th. And there are some good software available for doing things like this. So here we've got a half times a third. So if we complete the rest of the sheet of paper, there we can see. And then if we fill in the same shapes throughout, we find that it is 1/6. So again, rather than just learning what you do, that you multiply the numerators together, you multiply the denominators together, they can actually see how it works. A more complicated one, 5/7 and 2/3. So what do you multiply together? And this is an area that does cause problems to learners, doesn't it? How do you multiply those two together? And so there we have the 5/7 and the other 2/7. And then we have the 2/3 and the other third. Complete the piece of paper. And what is the area that we have there? So if we fill in all the different sections, we can see that we have 5/3, so we've got 21, and we've got 10 of them that are shaded in. So we have 10 21sts. So this helps with thinking things through, understanding for the learners to be able to do. And then my seventh thing that worked for me is to create connections. We do need to link topics together, and a lot of maths has been taught as separate things. And we need to move away from that, encourage learners to look for links in topics. A diagram can give understanding to some. So, for example, an equation like that, coming up with a picture like the one there, where we have on the top left, we have the x by x, which of course multiplies together to give us an area of x squared. We have +3 along the top, which is 3 by x, so that is 3x. Bottom left, we have 2 by x, so that's 2x. And the bottom right, we have 3 by 2, which gives us 6. So we can see how to multiply out the fractions using the ideas that we've used previously for area. So this can really help learners to understand multiplying out using algebra. Simultaneous equations and graphs are another thing that I didn't discover until I think I was probably in adulthood. I learnt how to work out simultaneous equations. So faced with an example like this one here, 3x plus 4y equals 29, 2x plus 5y equals 31, I would then think, well, yeah, if I get 6x, if I multiply the first one by 2 and the second one by 3, I can then subtract one from the other and I can get a value for y, and then I can substitute back in and get a value for x. It was a technique that I learned. I had no idea what it was about. I didn't know that I was trying to find a value which was correct for both equations. What value for x and y was right for both equations. Even though it used the word simultaneous equations, I never associated what simultaneous meant with any other aspect of life. But then I realized when you draw them as graphs, you end up with two straight line graphs, and the place where they intersect is the place where they both have the same value. So you can see in this particular example that when x is 3 and y is 5, then it meets the criteria for both equations. So simultaneous equations, straight line graphs, they're linked, and yet many students never see that, never understand how these things work together. Another one that I discovered more recently was pie charts and box plot. Now, I'm not suggesting that you teach this, but it's just an example of how things can be linked together, how we can show that there is a link in all sorts of areas of maths. So here we've got one where we've got so many 9s, so many 10s, so many 12s, so many 13s, etc. And they've been filled into a pie chart. And if we were to do a box plot, we would want to know where the median was, which is at the 6 o'clock position. So that goes to number 14. The first quartile is the 3 o'clock position, which is 12. And the third quartile would be at the 9 o'clock position, which is going through 17. So we can actually see a nice example there with a pie chart. Of course, it doesn't work with most pie charts because they're not doing things in numerical order. And what is the value of that particular pie chart? I'm not sure what it actually shows, but it gives an example of another link that there is between different areas of mathematics. So going back over the 7 things that work for me: use non-calculation starters, give them a reason for learning, start with a problem, not a method, don't repeat what they already know, use collaborative learning, reasoning rather than correct answer, and create connections. Fiona mentioned this morning the 8 principles for effective teaching that the late Malcolm Swan came up with when he was doing his work on collaborative learning. And here are the 8 principles, which are related to the 7 things I mentioned. Build on the knowledge learners bring to sessions. Expose and discuss common misconceptions. Develop effective questioning. Use cooperative small group work. Emphasize methods rather than answers. Create connections between topics. Use technology in appropriate ways and make sure that they can see it, not like I did, and use collaborative tasks. That's the end of my presentation. My name is John Barton. I'm the chair of NANAMIC, the National Association for Numeracy and Maths in Colleges. You can contact me at chair@nanamic.org.uk. And can I also say, if you're not a member of a maths association, I encourage you to join one. Find the one that is appropriate for you. And if you're post 16, I would suggest NANAMIC, obviously, but do join an association and get yourself involved there. Thank you.
Thank you very much to John for fascinating talk covering a huge amount of territory there and some really good, really pragmatic ideas. Just in the chat there, I saw somebody asking, get a question of the PowerPoint. John will be contacting all speakers after the conference is over and asking if we can share slides on our website. So basically to everybody, please watch out. We'll be sharing such material as we can. Yeah, so we've got a couple of minutes, I guess, for any questions. I know there's a bit of interaction in the chat, but if anybody wants to ask John anything just now. I mean, I'm going to be the person who asks the question that indicates they spent less time listening than they should have done at school. What is the difference in a segment and a sector?
Ah, right. We usually think of segments as being like an orange segment because we take it out. So the one that actually goes into the center is a sector. If you lay an orange segment down on its side, that really looks a bit more like a segment. does. So it's sort of a line going across a straight line, just from one part of the circumference to another part, not one that goes through the middle.
Thank you. I should say that I was well into an undergraduate degree when I learned the difference in a disc and a circle as well. So I'm obviously a slow learner here. Well, question in the chat, the hardy perennial. What would you say to a student who asks, when will we use this in real life?
Yeah, I think that's a valid point, depending upon the particular learner. I think one thing that I have done is some maths is just beautiful. Some maths just has pattern to it. And, you know, if somebody says, what is the point of this? Then I will say, well, what's the point of, you know, a pop song, or what's the point of a painting, or, you know, oh, because it makes us feel good, or something like that. You know, what is the point of some of the many things that there are in life? So sometimes we just need to appreciate the beauty. And I certainly find beauty in lots of maths things. But I think it is a valid point. And one thing that I would love to see is that we make that distinction between the numeracy skills that people need for life and the subject of maths, which is different. We make distinctions in things like language, where we talk about the skills of being able to read and write and so on, as opposed to understanding about literature. We do make that distinction. We don't tend to in mathematics, and there is a big difference. The maths that you're going to use later on, maybe at university, is quite different to the maths that you need for everyday life.
I remember a student, a new first-year student at university, who'd just done a first course in proof, telling me with some indignation, this is really interesting, but it's much more like literature than mathematics. Maybe that student was onto something.
Yeah, quite agree.
Well, thank you once again, for really interesting talk.
Thank you.